Welcome to Knowledge Platform. Subscribe our channel. Your subscription motivates us for more hard work. Today our topic is Gauss Law. The total of electric flux out of a closed surface is equal to the charge enclosed divided by the permittivity. As you can see in the figure that phi is equal to q over epsilon naught. We have applied Gauss law on a spherical closed surface. The sum of the flux is proportional to the total charge enclosed. We have cut a patch from this closed surface and apply the Gauss law on that surface. So del phi is equal to E del A, where del A is called vector area, which is perpendicular to the electric field. Permittivity is defined as the proportionality constant that relates electric field in material to electric displacement in that material. The electric flux through an area is defined as the electric field multiplied by the area of surface projected in a plane perpendicular to that field. Gauss's law is a general law applying to any closed surface. We see here that Gauss law is applied on closed surface. It is an important tool since it permits the assessment of the amount of enclosed charge by mapping the field on a surface outside the charge distribution. For geometries of sufficient symmetry, it simplifies the calculation of the electric field. Now we explain the Gauss law in integral form. Here we can see that in a figure we have a closed body or closed path of a irregular shape, and we have to apply Gauss law on this closed figure. We see that electric field pointed outwards and dA is a vector area which is perpendicular to the electric field. So integral E dot dA is equal to q over epsilon naught. The area integral of electric field over any closed surface is equal to the net charge enclosed in the surface divided by permittivity of the space. We know that Maxwell equations, the four fundamental equations of electricity and magnetism. Gauss law permits the evaluation of the electric field in many practical situations by forming a symmetric Gaussian surface surrounding a charge distribution and evaluating the electric flux through that surface. Electric flux. The concept of electric flux is useful in association with Gauss's law. The electric flux through a planar area is defined as electric field times the component of the vector area A perpendicular to that field, that is phi is equal to EA cos of theta. If the area is not planar, then the evaluation of the flux generally requires an area integral, since the angle will be continuously changes, that is phi is equal to integral E cos theta dA. Now we study the applications of Gauss's law. Gauss's law is a powerful tool for the calculation of electric fields when they originate from charge distribution of sufficient symmetry to apply it. Here are some examples. Point charge, conducting sphere, surface with uniform charge density, line charge, conducting cylinder, cylinder with uniform charge density, sheet of charge, charge on surface of conductor, charge conducting plates. We can apply Gauss's law on all of these surfaces and can find the electric flux. Thank you.